Antonia Carzaniga will give us a lecture. Dr. Antonia Carzaniga is an assistant research professor in the Department of Computer Science at the University of Colorado at Boulder, and has recently joined the Faculty of Informatics at the University of Switzerland as an assistant professor. And he received his laureate degree in electronics engineering from the University of London in 1994, and the PhD degree in computer science from the same university in 1999. Professor Carzaniga has conducted research and published papers in the areas of content-based networking, distributed and published subscribe systems, software configuration management, code mobility, and software process. Dr. Carzaniga.
Thank you. Okay, so today's talk is about content-based networking. So the first thing I'm going to do is to introduce the idea of content-based networking, and I'm going to do that by contrasting this idea with the traditional, what happens in traditional networks. And this is a gross oversimplification of what networks are about. But if you really think about it, they're about two kinds of services. Something that is essentially a telephone type service, and something that is essentially a postal service. What this means is that you have a network, and you have a bunch of applications, a bunch of clients in software parlance of this network. The applications connect to the network, and they're configured with a number, an ID. It could be a street address, it could be an IP number, it could be anything you want, but it's an identifier that tells the network who they are and where they are. And what the network does, it delivers information to those clients by using the ID associated with the message as posted by the sender application. So the sender application says that it wants to send information to client number 456, and then it goes to 456. Okay, so this is the main idea. Now, this is a very successful, extremely useful service. Traditionally, it's been used for basic communication, personal communication, email, to implement applications such as the World Wide Web, hypermedia, and distributed computing, RPC. So the address-based model is very popular and very successful and very useful. However, it has some fundamental features that are also limitations. So, for example, its sender is in control. The sender is essentially telling the network where to send that information by specifying the address. And there are other application needs that need to be met in advanced networks or advanced applications. You want the receivers to be more in control. You want the receivers to be able to tell the network what they want, and because they want the network to deliver only the information that they need when they need it. Also, you want the receivers to be in control in the sense that the sender don't need to know who the receivers are and where they are. And also, you need information to go multiple places. So you need inherently multicast communication. So the main idea of content-based networking is to do this by sort of changing the configuration process of the network and reversing enhancing the network service interface with this content-based service model. Now, the service model, okay, so the idea is that instead of having numeric or some form of ID, applications declare their interest. They say, I'm interested in information like this, okay? And they say that by posing these things called predicates. Predicates are simply conditions, okay? So they say, I'm interested in information that matches these conditions. So they advertise predicates. In the example here, we have application 1 advertising predicate Q, the symbolic identifier for predicate. Application 2 advertising predicate P. Application 3 something that is P or Q. Okay, and senders simply inject messages into the network. So they simply send. Okay? The send operation, the semantics of the send operation is deliver this piece of information to all the receivers that have matching predicates. Okay, so in this case, if M happens to match P but not Q, then it should be sent to application 3 and 2. Okay? Does it make sense? All right. So this is the idea. And this is sort of a list of, just to give you an idea of what kind of applications might use this network service. Intrusion detection, service discovery and brokering, for example. And the one up at the top is sort of a generic form of that. Is another way to call content-based networking, is something known as publish-subscribe communication. Okay. Obviously, I'm not going to talk about all of this, but just to give you an idea that this is a the content-based networking model is useful for a number of applications. So what's the essence of the idea? Well, it's to implement that communication model as a network. Okay, with all the features of a network and with all the typical design approach used in building networks. So design a network based on an network architecture, based on a routing protocol, forwarding protocol, etc. So this is what this work is about. The host interface, just to be extremely simplistic in this situation, is essentially consists of the two functions that we already described. Set predicate is the one that allows applications to advertise their predicate, and send message simply sends the message. It injects the message into the network. And for practical assumptions, I'd rather not get into this whole discussion, but it always pops up. So is this an overlay network? Is this a real network? For obvious practical assumptions, right now we're thinking of implementing this as an overlay network. Okay, but it doesn't have to be conceptually. So with this idea, we at Colorado, Alex Wolf and I and some of our students developed essentially these two foundational pieces of the content-based network. One is a routing protocol, which we presented at InfoComm this year, and one is a forwarding protocol we presented at SIGCON last year. So these are sort of the foundational protocol. In this presentation today, I'm going to go over the first one, the first protocol, and then talk about another issue, which is privacy in this network. In fact, this is the outline. I'm going to give you the general routing and forwarding strategy behind this routing protocol, and then go into the detail of how it works, how the specific routing scheme works. And then I'm going to talk about privacy. Privacy is important because this content-based routing, content-based networking service exposes the content of messages and the predicates and the receiver's intentions, what they're interested in, their interests. So it introduces some privacy issues that are not common in address-based networks. So I'm going to talk about a scheme that addresses that. So here we go. Okay, so this is the animation explains the general routing strategy behind this routing protocol. We have the nodes and the links. As I said, this could be overlay links right now, but it doesn't really matter. And we have two nodes, nodes number 7 and nodes number 9, that declare some predicates. So they are receivers. They have some applications there that wants to receive data. Okay, so they set their predicate respectively to Q and P. Now the routing protocol propagates those predicates all over the place and sets up, as usual, what routing does, it sets up forwarding state within the network. It installs those stable. So for example, in the picture here we have the table associated with router number 5. That table says that the interface to router number 9 is associated with predicate P, and the interface to router number 7 is associated with predicate Q. Okay? So the routing protocol, and this is half of the presentation, is going to spread that information around and construct that forwarding state. Okay, so we have that forwarding state. Once we have that forwarding state, we need to forward messages according to that forwarding state. And the idea here is essentially to use a two-layer scheme. The first layer is a broadcast layer. So we treat every message as a broadcast message, something that needs to go everywhere. Okay, it's the basic layer. On top of the broadcast layer, we prune the propagation of this broadcast packet to only the nodes that are interested in that message. Okay, if it was just a broadcast layer, it would go everywhere, but we don't send it everywhere. We send it only where nodes are interested in it. In this case, 7, or let's say it goes to 7 and 9, we send it down the path to 7 and 9. So essentially, we treat a message as a broadcast message, but we only follow the content-based routing part that was established by the routing protocol. Is that clear? General idea? Okay. So that's why we call this the combined broadcast and content-based routing scheme, because it combines a broadcast layer with a content-based layer. Okay? We treat packets as broadcast packets, and then we only follow the paths that have content-based information in it. Okay. The broadcast layer, obviously it's a very well studied and well known area. It's very clear how to create broadcast layers. In addition to the traditional requirements of a broadcast layer, that is send the packets everywhere, we have additional requirements which we talk about in the paper. I'm really not going to talk about this specifically, but you might be able to see it in when I explain the use of the broadcast layer in the protocol. The protocol uses the broadcast layer in a way that it requires specific properties, okay, for this broadcast layer. And then we have the content-based part of the protocol, which is most of what I'm going to talk about. That uses essentially two mechanisms. One is a push mechanism called RA, that stands for receiver advertisement, that pushes those predicates out from the receivers out to all the potential senders. Okay, that's first part. Second part, it's kind of a pull mechanism that does a broadcast and then a converge cast back to all the receivers, all the senders. That's why it's called sender request update reply. It asks for who wants what, and then it synthesizes the protocols backwards. So it's a broadcast, converge cast kind of thing. So we have these two mechanisms, and these two mechanisms are the core of the CVCB, or at least the content-based part of CVCB. So let's talk about the receiver advertisements first. The idea is that whenever a node advertises a predicate, you have to let the network know about it so that all the potential senders can follow that through, right? They can send messages that match that particular predicate back to the receiver, okay? So this is what we do. This is, again, an example. Node 6 is advertising predicate P6. So what happens, we use the broadcast layer to push that advertisement out to all the other nodes. And in doing so, we leave state. We install forwarding state. Okay, this is intuitive, isn't it? Somebody asks for some information, you broadcast that request out, and everybody remembers that they're asked for that information. Okay? Okay, this is the essence of it. Before I go forward in explaining how this protocol works, I have to introduce the concept of covering relation. Okay, because we're talking about content, we're talking about selection over content. Predicates are essentially Boolean functions that say whether a message is of interest or not. Okay, so they're like a query in a database. They select information of interest. Now, selections have relations. They have inclusion relations. So if you're interested in the subset of information that he is interested in, then that means that your query covers his query. What that means is that the query optimizer or the routing scheme can take advantage of this covering relation by routing information first to you and then to him, or by masking his request because it's already covered by your request. Okay, this is going to be hopefully clear in 2 seconds. So anyway, there's this covering relation that is purely a subset relation between the predicates. So if a predicate P describes this set of messages, matches this set of messages, and predicate Q the larger set of messages, then we say that Q covers P. Okay, that's all. Simple. Okay, how do we use this relation? Well, if you paid attention to the previous slide, we said that we broadcast receiver advertisements everywhere. That's inefficient. We don't want to do that. We want to limit that as much as possible, because every receiver, every advertisement now is going to be broadcast everywhere. So the way we limit that broadcast is by exploiting this relation. And here's exactly what we do. We propagate the request up to the point where it's already covered by previous requests. It's a caching scheme, sort of. And here's the example. We have node 6, again, that has propagated its request before, as in example before, and it has left state on node 4 and state in node 3. Okay, the intuitive state. Okay, interface 6, predicate P6, interface 4, predicate P4. Okay, because information needs to go here and then here. Okay. Now, what happens if node 2 comes along and advertises predicate P2, which happens to be covered by predicate P6? Where does P2 go? It's propagated everywhere? Well, no, it's not propagated everywhere. As soon as it hits node 3, it would add state to interface I4 that is already covered by the previous state. What does this mean intuitively? It means that node 3 already knows that it's going to have to forward things matching P6 down that way. Okay? So by adding P2, which is already covered by P6, you're not gaining any information. Okay? So you don't need to maintain that additional information, you don't need to process that, you don't need to forward it. Okay? So the idea is all the operations in the RA protocol block whenever you hit a covering, a point where the covering relation holds. Okay? So that's the main RA protocol. This protocol happens to work, actually, just so you know, this protocol has cases in which it's broken. As I was telling some of you guys last night, we know that this protocol has some situations in which it doesn't completely work, and we're working on it. But the main point I was trying to make here is that this protocol has an inflationary effect. So it inflates the predicates in those tables because it can only add to the tables, right? You stop whenever you are covered by something else. What if you want to remove things from those tables? What if you're not interested anymore in those messages? If you push out a predicate that is smaller than the ones that you pushed out before, that gets blocked, right? So the effect of this is that predicates can only inflate in those tables using the RA protocol. So the CBCB scheme is equipped with another set of protocols that are designed to balance the effect of the address inflation produced by the RA protocol. Before we talk about that, I'm going to show you that this is in fact true, that there is an inflation. The example is simple. Let's say that P6 is now, the application running on node 6 decides that it's not interested in things anymore. You have a question? It's not interested in P6 anymore, and it's interested in a smaller set, P6 prime, that happens to be smaller, so covered by P6. Well, by the covering relation rule, that advertisement gets immediately blocked at node 4. It never gets propagated, right? The effect of this is that 4 is going to send messages to 6 that 6 doesn't want. Okay? It's going to send messages that match the old predicate, P6, but they don't match the new predicate, P6 prime. Okay, this is what we call content-based address inflation. Now, to counter that, yes. The covering relations are actually found in this case in a very simple way. There isn't an explicit way to find them, but if you, just a second, if you look at the way that that the RA protocol updates the tables, it uses OR, it does junction. So if you add a new predicate, say in this case you add P2 to the predicate associated with interface 4, okay, so what you would say is the predicate associated with interface 4 equals P6 or P2. Make sense? No? Okay, you're adding a predicate. That means that you're adding in the sense of a logical disjunction, okay? If that predicate, when you add it to it, so you add it as an OR, equals the predicate that was there before, it means you added nothing, okay? How does it equal that? In the actual implementation, we run this through a simplifier, logical simplifier, that says, okay, X or Y equals X, so Y didn't add anything, right? Right?
For example, if it stopped here, if later, I mean, the path will separate. I mean, for the two different messages, for these two contents. So what we have, I mean, will this create any problem? I mean, for example, in this case, if a new predict 6,
Yeah.
is covered by P2. Okay, P2 is covered by P6, right?
Yes.
And so P2 will not go further than
Yes.
P6, right?
Yes.
Okay, so this means absolutely the destination P6 equal the destinations, all the destinations of P2.
Yes.
Okay,
Yes.
and done that.
Okay. This, I'm not sure that that's where you're going, but this is the reason why this protocol in some situations doesn't work, because not all the trees that come down from P2 correspond to all the trees going down from P6. And there are some cases in which it doesn't work. And this has to do with also the conditions that the broadcast layer has to, because these two are sent using the broadcast layer. So yes, there is a problem in some situations, but in this situation, the protocol doesn't send things down that way anymore because they don't need to. I mean, this doesn't need to be updated because this information is there already. Okay.
Yeah, I just wonder whether there's some case that the revenue divert later.
You're talking when somebody updates these predicates, P6 and...
I mean, the current relation, for example, is only in the intermediate region, the current relation, and after that, it diverges again. Is there in some case? Like overlap. Two regions are overlap, not totally current.
Yes. Oh, this is fine too. This is taken into account here. When you do the addition of the predicate, you add the predicate carried by the RA to the existing predicate, and you simplify. By doing this, you create a predicate that is the union of the two. So if something comes along after that is covered not by the individual ones, but the disjunction of the two, this is also covered in this case. Okay. If I'm not answering the question, maybe we can follow up on this.
In the first phase that you propagate your forward mixture for propagating basically the predicate.
Yes.
Right? So you do it all over the network. So
Yes.
Almost every node in the network knows the predicate is associated with
Yes.
Receiver nodes.
Yes.
Right? Then in the sending phase,
Yeah.
you broadcast and you try to filter out the flooding caused by that broadcast based on this information,
Yes.
right? But this information is not unique on particular nodes. It's almost everywhere in the network. So it's sometimes I think how this filtering out works. How doesn't it lead to flood?
You only follow the links in the broadcast path of the sender now that have matching entries in these tables. That's what you do.
Yeah, but
Yeah, but not on all interfaces. If you go to the, let me go back here. The idea is this. The black arrow represent that forwarding state, okay? This sort of bicycle things represent the broadcast of the sender. You only follow the ones that are combined. So in this case, the broadcast will send you to 4, but 4 is not interested in receiving that information.
why doesn't 4 have the predicate states information?
It does, but it has it on different interfaces. In fact, in this case, it's 2 that has it, but it doesn't give it to 4. It doesn't send it to 4. No?
So there's always a unique path you send from the sender to the receiver.
The broadcast layer has to be such that the receiver path broadcast intersect the sender broadcast in a single path. It has to be single if it intersects because they're trees. So if you have 2 of them, you got a problem in the broadcast layer. But if that condition is met, as in this case, then you simply follow the broadcast tree from the receiver side, from the sender side, intersected with the one of the receiver side, and you're fine.
The point that I don't understand is how you prevent those forwarding sections corresponding as
Yeah.
not to be everywhere in the network.
They are everywhere in the network, but they follow the broadcast path. They construct the tree that converges onto, say, 9. So the state relative to predicate P produces essentially a tree that converges onto 9. It's a tree, okay? Now, what you have to do is to combine the receiver predicate broadcast with the sender broadcast.
Between different routes.
Yes, and they intersect in a route that goes exactly from the sender to the receiver. Okay? I should move on because otherwise I'll never get through the presentation. But you know, we can talk about it later. So as I said, there's this content-based address inflation. We counter that with a proactive broadcast convergecast sort of request-reply type of protocol that is this time initiated by the senders. Okay, and how does this work? Well, it's easy. As I said, broadcast, you send this request, the request goes out, say, hey, 5 wants to know what the predicates are around the network. What are they? Well, every node responds, they produce as I said, they do a converge cast, they go back to 5, and going back to 5, they assemble the predicates. So if 2 has predicate 2, 6 has predicate P6 prime, then this is P6 prime or P2, this is P6 prime or P2, and this is P6 prime or P2 or false, which is P6 prime or P2. Okay, what this does, it essentially updates the table to counter the effect of the inflation produced by the R8 protocol. Okay, this, as you can obviously imagine, is also inefficient. Why is it inefficient? Well, because it's a broadcast converge cast. We gotta go to all the network and back. But there are ways to optimize it. I'm not going to go into that. There's options and optimizations possible on this protocol as well. They depend on the type of broadcast that you use. Just as a general comment, notice that if you use a single tree to implement the broadcast, so if the broadcast is implemented as a tree, as a single tree, then you can greatly reduce all this traffic. Because a single broadcast will serve an update for all the nodes. Okay, Can't possibly tell you exactly why, but it's actually easy to understand. Also, in the simplification, we can use logic simplification. So we can greatly reduce the amount of information we have. We don't have to sum all the predicates. We can simplify them, going backwards to the root. And this is an example in which, as I was saying, you can reuse things whenever you have a bridge in the broadcast. Now, notice that again, if you use a single tree, every link is a bridge. So you can simplify every path, and you can reuse every path. Details are in the paper, and I'd be happy to hang around and chat with you about it. So anyway, we did this implementation and we evaluated it. We evaluated along three main lines. One is the functionality, filtering, and protocol scalability. Functionality means, does it send the information where it needs to send it? Okay, number one. Number two, filtering. Well, does it send, because if you have a broadcast, that certainly works for that, but it also sends a lot of other information that you don't need. So filtering, does it filter the information? Okay. And protocol scalability, how does the protocol behave in the face of scale, large networks, or changing predicates, and those things. And we essentially, on the main functionality, this is a good result. It means that once the information is propagated through the array protocol, it essentially stays to zero. On the y-axis here, you have the false negatives, the amount of information that should have gotten to some receivers but hasn't. Okay, because of some predicates propagating, not being yet available at the end of the network. As I said, this is what we've seen in our experiments, but in some cases we are able to construct situations in which this is not zero. Every once in a while, there are some situations in which you have false negatives. So, which is bad. Yes.
Connectivity is not considered here.
There's yes. We excluded that case. If the network gets cut, or the overlay gets interrupted, there's nothing I can do to get the information out there. This is the counter of the previous case. This is a false positives, things that you get that you're not supposed to get. And some of this might be, so you see some fluctuations, some 10% of the traffic is false positives, okay? Again, we are not completely sure what's causing this. Chances are a fraction of this false positive traffic is generated by the fact that there's fluctuation in the predicates and there's inflation, in the array protocol. It takes time for the SRUR protocol to counterbalance that inflation, and therefore you have false positives. Okay, that's part of it. Another part of it is that, again, we know that there are some situations in which some specific forms of topologies that cause also additional false positives. Okay? And this is the control traffic stability. On the y-axis, we only have RA traffic. We also have studies with SRUR traffic. And this essentially shows that it's stable. The absolute values are scary. So in this case, we have 40% of the whole traffic in the network is control traffic. Bad. But this study was done to explicitly emphasize control traffic. In fact, we have extremely low message traffic. Over the whole network, we only have a constant 40 messages a minute in the whole network. Who asked the question? How large is the network? I think in this case it's either the 200 node or 100 node network we experimented with.
Do you have a relation between the network nodes, the size of network and the...
Yes, we do. There's, I can show you that later. But essentially it is stable with respect to that as well. What is not stable is the SRUR traffic. SRUR is essentially, in the worst case, increases with n square. But why n square? Because you go n 2 times, and you have to do it for everybody. Okay, so that's n squared. But that is stable also. And again, as I said, these values are, in absolute terms, are in fact very low if you assume a reasonable network where there's a reasonable amount of data traffic. Okay, so the relative values seem scary, but they're actually not that bad.
Is this a web network or a wireless network? Is this wireless network or wired network?
This is a wired network constructed using a wire network model. I mean, as I said, this is a simulation, but the network model we use, this is a wireline network.
What does no change mean?
In the first case, this is traffic in an example in which applications never change their predicates. So there's no control traffic because it doesn't need to change. Okay, and in this case, they change their predicates every 5 minutes, every node on average. And in the blue, in fact, it's a little higher. And the green, they change every 10 minutes. Okay, you have control traffic when nodes change their predicates. Okay, there's no control traffic at steady state when they don't. Yes. No, that's not a false positive. A false positive is we counted it in the simulation as packets that get to a dead end. So if you're forwarding things along a path and at some point you just drop it on the floor, you forward it for no reason. That counts as a false positive. If it reaches a destination after a potentially long path that goes through 75 relay nodes, that's not a false positive. That's a good packet. It sends from a source to a destination where you wanted it. The fact that it goes through other nodes is an artifact. I mean, it's a product of a routing scheme. This depends on how you implement the broadcast layer. The broadcast layer is stupid. If it's say implemented as some sort of cycle, okay, then you're not optimal. The way that we implement it in this scheme is actually not optimal in the sense of the Steiner tree, but optimal in the sense of the shortest path tree. So the end-to-end is optimal. The global may not be optimal. The way that we did this is by implementing a broadcast layer that constructs per source shortest path spanning trees. Make sense? I know that because between me and the students that work, that's the part that I implemented. So anyway, conclusion on this part. If you believe what I said, we have a generic routing protocol for generic networks that is based on 2 ideas. Generic in the sense that it supports multiple, any kind of topology. And any kind of, I want this, I want that. So actually the interface is pretty generic. It makes very little assumptions at the service level. It does assume an underlying broadcast layer, but as I said, the techniques exist to implement that. And it's based on a push-pull routing protocol for the content-based part. And the software is available, so you can download it. Okay, and the papers are available also. Yeah.
Can you get rid of much of the network traffic just by discarding the predicate and after a certain amount of time, not using SIUR protocol?
We thought about that too. We thought about it, but then you have to push the arrays periodically also. Yes. It's a trade-off. We have not experimented with it. We thought about it. It's a trade-off, as I said. If you want to be extremely well, you would have in a case like this, the red line wouldn't be flat here, right? Because you would have a constant amount of network traffic, even if you change nothing. And I don't know. I mean, it depends. We haven't thought about it. I mean, we thought about it, but we haven't experimented with it. It's a valid strategy.
You could also save the amount of memory at each node, right?
I don't see that.
I mean, when SI SRUR is used, let's say a router in the network, doesn't the router wait for all the URLs?
Oh, yeah. The SRUR has some temporary memory that it uses to assemble the predicates. Absolutely, and that's done with a timeout. I don't believe that is a factor. I mean, it's true, but I don't see that as a major cost. Yes. It's loop-free by definition if you think that the broadcast layer is loop-free. You only go through the broadcast layer. Yes, but you send the messages. I see what you're saying. Absolutely right. If you were to follow the receiver trees and you have more than one tree, then yes, you could have loops. But remember, you're also following the sender broadcast. So you're not sending things outside of the sender broadcast. So if the sender broadcast is loop-free, you're loop-free. Okay? Now, in 4 minutes, no. Let's go to, okay. As I said, though, we know that that protocol has some issues that are related to the interaction of the broadcast and this content-based part. But actually, it also works. I mean, we also know that it works for most of it. And the implementation is available. You're welcome to try it and play with it. So now I'm going to sort of switch gear and talk about privacy. Now, if you think about the network model that I just described, where people ask for information, the information gets messages and delivers those to the interested parties, this exposes the interests of the receivers. So it introduces a privacy issue. Just to get rid of the other security issues in this context, consider that the usual authentication and integrity can be solved with traditional techniques. You know, you can sign messages, you can MAC messages. It's a known, you know, there's known techniques to do that. So I'm not interested in those. What I'm interested in is the difficult part, is the privacy. And think about it in terms of the service. Again, privacy is directly counter to the service model. So if the service is about receiving information that you asked for, well, you can't ask for something and then expect that the network doesn't know what you asked for. Okay? So there's a fundamental clash between the privacy goals of the receivers and the goals of the receivers in using the content-based model. So how do we deal with that? Well, first of all, let's model the content-based network in abstract terms and figure out the proper setting. This is an abstraction using the usual parties, Alice and Bob, the sender and the receiver. And this time we have to add a content-based network in the middle because it's mediating between Alice and Bob, okay? So Alice sends a message, Bob sets a predicate, and then receives a message because the predicate matches the message. This is the basic simplistic model. What is the privacy goal here? Well, in very simple terms, is to make sure that this happens without the CBN knowing what the predicate is and what the message is. Okay, we want the message to be garbage or pseudo-random for the CBN. We want the predicate to be pseudo-random, and yet we want the predicate to be matched against the message and the message forwarded along. How do we do that? Actually, this is the situation. Also, we assume, because we have to do it in this case, that Bob and Alice share some key material. Otherwise, we would have to send the message in plain text, and we wouldn't be able to do anything. Does it make any sense? Question?
Why is the key should be private? I mean, why you?
Let me give you an example. This system is used as an intrusion detection system, where you tell the network that you're interested in receiving alerts from other systems that are related to vulnerabilities in your network. Would you be concerned about telling the networks what your vulnerabilities are? I would. Another example, you are a user interested in, I don't know, some kind of publications or some kind of medications or some kind of information. would you be willing to tell the network that you're interested in that information? You know, and the FBI will knock on your door and ask questions. It's annoying.
What about the fact that even if you, for example, had the image in somewhere, so again, you know, you can send primitive,
Primitive, you mean predicates? Yes. You can find out that the two of you have the same. Yes, this is an issue in this particular model. It's not necessarily true if there's different parties. Okay, in this simplistic model, it doesn't exist because you don't have two senders and two receivers. All right, so it's outside this simplistic model. In the more complex model, which I'm not going to talk about right now, it does. You have that problem, but you can also counter that using some cryptographic scheme on top of this scheme that I'm going to describe right now. It's not too hard. All right. So, given this assumption, the goal is to have Bob send a predicate that is essentially pseudo-random for the network, indistinguishable from just garbage bits. Same thing for the message. Alice sends a message that the network doesn't understand, and yet we want the network to be able to do the matching and forward the message along. How do we do that? Let's skip through the approximate solution. Okay, the approach is the following. We take the message and encode it using some function x sub k dependent on the key bits into m prime and y to encode the predicates, with the obvious constraint that if there's a matching between the message and the predicate, the same relation is preserved in some ways, okay? Such that, in other words, p prime of m prime corresponds to that, and such that, because this, okay, so what kind of function would work in that case? What kind of x and y? The identity, well, hash function wouldn't necessarily. The identity function would work, but it would reveal information. So the extra constraint is the security part of it. Okay, the first one, the first bullet here is the functionality. Okay, we want functionality to be preserved. We also want security. We want p prime and m prime to reveal the least amount of information as possible from the network. And the method is using an encoding scheme that uses a form of hash functions called Bloom filters. You guys know what Bloom filters are? Maybe, maybe not. Okay, so before I go there, let me tell you, I didn't tell you, okay, so you bought my whole rest of the presentation without knowing what messages and predicates look like. In fact, that's the beauty of that scheme. It's sort of agnostic of what kind of messages and predicates you have. It assumes that you can compute logical implications or those kind of things. But so here's an example of a message. A message is essentially a set of attributes. Attributes have names and values. It's intuitive, so I'm not going to spend time describing it. A predicate is also intuitive. It's like an SQL query, essentially. It's a disjunctive normal form of a logical expression. So the first one, the first conjunction, which we call filter, contains two constraints. The first one says alert equals connection refused, and the second constraint says port less than 1024. Okay, so these are the kind of predicates that you can pose. So how do you use Bloom filters to encode predicates and messages? If you know what Bloom filters are, we can skip over this part. Actually, let's go through the example. A Bloom filter is a bit vector that has bit positions that are initially all zeroed, and that you fill using hash of the values. A Bloom filter is a short, concise representation of a set. Of a set of what? Of a set of anything. But in this case, a set of strings, okay? So for example, we have the set of strings chow, foo, and bar, and we want to encode that in the Bloom set, in the Bloom filter, I'm sorry. And we use two hash functions, h1 and h2, that are supposedly independent. So the first thing we do is we push the first value into the first two hash function. The two hash functions produce a value that is between 0 and 9. Okay, so they essentially give us a position in the bit vector. So we flip the bits, we turn on the bits. Okay, what do we do then? Well, we do the same for foo. We turn on the bits. Bar, we turn on the bits for the hash function. So now the bit vector 0011010101 represents, it's a concise representation of the set chow foo bar. What can we do with that set? We can do, we can verify that something either belongs or doesn't belong in the set. Okay, that's the test that we can produce with Bloom filters. How do we do it? Well, we push the same thing through the function, through the hash function, and figure out that the 2 bits are already set. So we answer yes. Okay, it's in there. In fact, it was. So we say yes. ABC, we push ABC through the network of hash functions, and it gives us 2 positions. This one is set, but this one isn't. Okay, so we can conclude for sure that it wasn't there, because if it had been there, that bit would have been set. The problem with Bloom filters is that they have false positives because they compress information. So in the case of XYZ, chances are that XYZ is going to hash with hash 1 to position 7, hash 2 with, or vice versa, position 9. They're both set. So we answer yes in our test, but yes is a false positive test. Okay, so this is a crash course in Bloom filters. How do we use that? How do we use Bloom filters? Well, let's go back to the idea. The idea is to take the message and take the predicates and encode both of them so that we can come up with a matching function. How do we do that? Well, we do it this way. We do it in 2 steps. First, we encode a message into a set, because we have to represent sets with Bloom filters. And the same thing we do for predicates. And the matching function, sets of strings, by the way, but it could be anything. The function that we use is the subset function. In other words, a message M is encoded into a set S of M, and a predicate P is encoded as a set of string S of P, such that if the predicate matches the message, then we also have that the set of M is a superset of the set of P. Okay? And then we represent them as Bloom filters. Bloom filters where we use hashed functions that are keyed using the key, and that's how we get the security of it. Okay? The key point in the two functions that produce messages, that encode messages and predicates, is to come up with the set of strings. How do we come up with a set of strings? Well, essentially for the predicates, we turn equality predicates into a simple string like this. You know, if the constraint is IDMF version equals 2, then we add the string IDMF version equals 2. Okay? For any other constraint less than substring subset, we turn them essentially into existence constraint. Okay, something that says there's some other constraint that isn't an equality on attribute IDMF. Okay, so IDMF version. So if we ask for IDMF version greater than 2, we can't be more specific, so we say somebody's asking about IDMF, so exists IDMF. That way, we can, and we can do that through all the constraints, so we come up with a large set of strings. And therefore, the whole predicate is the conjunction of those. And for the message encoding, we do the same, except that we don't choose one, we have to do both. Okay? So if we have a message that has an attribute that says IDMF version equals 2, well, this will produce the string IDMF version equals 2, and also the string exists IDMF, just in case we have to match all the other constraints. Okay? If this isn't too clear, don't worry too much about it, but it's easy. And again, we add the 2 sets and we put them together. Okay. So observation. Well, the matching function is simply a subset relation between the 2 Bloom filter. This is the #1 observation. Okay. If you want to implement this in C, just to give you an idea of how efficient this is one operation. Essentially, well, one bitwise operation and one comparison. Okay. So if the Bloom set of, say, 64 is implemented as an integer, figuring out that two integers are one the subset in terms of bit of the other is extremely fast. Okay. So this is very efficient. Okay. Another observation, which is crucial. I told you about covering relations in the protocol in CBCB. Well, in this whole encryption scheme, what happens if we lose the ability to compute those relations? The protocol doesn't work anymore, or at least the RA blocking doesn't work anymore. Instead, it does in this case, because Bloom sets, Bloom filters, represents set, and the subset relation represents the covering relation. So with the exact same operation that we can do the matching, we can do the covering in one shot. So this is extremely powerful. What's the bad part? I told you all the good parts. Well, the bad part is that there's false positives. So you introduce false positives in the process. Okay. Okay, let's conclude here. The idea is, again, to have a method to guarantee privacy in the world of content-based communication. And the approach is to use Bloom filters for the encoding of predicates and messages. I'm still working on ways to make the evaluation over large sets of Bloom sets, if that makes any sense for you. Using the idea is to use zero suppressed BDDs, which is a data structure, a binary decision diagram.
How do you, in the first step, how do you let the pairs of sender and receiver share the private key?
How do you do that?
Yeah, how do you set up?
Oh, I don't care. It's one of my assumptions. I assume that they do. You want an example? Okay. Let's say that.
I'm just wondering if there could be some security issues in this step, because if you just let them share the key in some setup procedures, and the content network in the middle, if it's getting involved in this process, by knowing that these two parties share the same key and refer information what if one wants something. So, for example, if the content network in the middle that knows that this source and this receiver share the same key,
Yeah.
then you can infer that some information about what is the receiver wants.
Actually, it doesn't know that. The network doesn't know that they share a key. They have to share a key in order to understand each other, but it's not necessary. You can also imagine this is most meaningful in applications where everybody shares the same key. So essentially, you have no information. This is useful where all the senders and all the receivers share the same key. Think about an application where you deploy the network in a hostile environment, but the users are pre-configured to use a specific key that is installed in them, before you deploy them. That is the most useful scenario. This isn't useful in the larger context of a network where you have parties joining in and leaving without a key agreement protocol, without another infrastructure. It's not. You have to agree on the key, but the fact that you agree on the key doesn't reveal any information.
I don't want to get into this.
Okay.
To get out of time.
Okay.
Just if everybody can get this key, then the central network can also get the key. If it's so easy.
No. It's not that it's easy to get it. I didn't say that. I said that everybody gets it. That's what we assume. Then you come up with a broken key distribution protocol, and the network can get it. Yes.
It's an assumption that there's no problem. So
I'm just delegating this problem to somebody else. I can't solve all the world's problem myself. But key distribution protocols exist. Do Diffie-Hellman. Between A and B. Who cares? I mean, all I'm saying is there's ways to distribute keys that some smart guys figured out. I don't deal with that. Okay, so conclusions. If there's 2 or 3 things that I'd like you to get away with today is content-based networking is this thing where it's a new communication paradigm. It's a new communication model where receivers ask for what they want, senders send, and the network gets them to talk to each other. So acts as a mediator. And we have worked on the basic foundational parts. We are still working on those, and it's a vast research and exciting area. There's new things that we're working on, stateful filtering. What does it mean to have a transport layer? Just to give an example. Sensor networks. We're working on a specific routing protocol that works best and nicely in sensor networks. Privacy, as I said, and you can find papers and all the software that I described, plus more, software in the forwarding part that I didn't have time to describe today. Essentially, the software that produced the first paper. No, first paper, just the paper. Second paper, it's just a position paper in a workshop. But these 2 papers come with software that is available from this site. So please go ahead, read the papers, give me feedback. Questions? Yes?
When you do the routing part, the routing protocol,
Yes.
if let's say receiver 1 and receiver 2, they are send the predicate, and one is a subset of another one, but we just do a simple logic operation.
Yes.
But under some situation, let's say you may have some deadlines. Let's say receiver 1 want to satisfy some deadline. The deadline of these 2 are.
Deadline, you mean expiration of the protocol?
I mean the packet from the information packet from the sender to these 2 receivers.
Mm-hmm.
So under this situation, you cannot do this like simple.
I guess I'm not understanding what you mean by deadline.
I mean the deadline of the information.
Some notion of QoS.
Yes.
Okay. Oh, yeah. If you block that, there's no way to distinguish between the 2. Absolutely. Yeah. Yeah, that wouldn't work in that case. I mean, yeah, that would not work. There's actually okay. Let me try to answer that question a little bit more. You can deploy some form of QoS or type of service or other types of things that are not included in a simple predicate. So let's say that you don't want, let's say you want to do rate limitation. This is, by the way, a feature of our sensor networking part of this protocol. You want to do rate limitation. So you say, I'm interested in this information, and I don't want more than 2 messages a second, because I don't care to receive more than 2 messages a second. Now this is some kind of information that you can propagate, and it's not a problem to aggregate that information as well. At each node, the only thing you say is, well, don't send more than this, and don't send more than this, and you leave that locally, and that filters out just like the content-based part filters information out. So if you look at it as a quality of service parameter, it can work. Other parameters might not work because you're blocking the propagation.
So, how do you handle the content scalability from, for example, if the number of predicts is very huge?
Yeah.
So in that case, the join table would be huge.
Mm-hmm.
And dynamically achieved, right? So,
yeah, this is, I mean, in the paper number 2 here, we present a forwarding function that scales to very large tables of millions of constraints. This doesn't mean that the scalability is not a problem. It is a research issue, and how you do that. But I mean, we believe that the covering relations is sort of the equivalent of the content-based subnet address relation. And so that can be used to limit the scalability problems that you mentioned. because essentially you're saving space in the tables by only looking at the superset of things as opposed to the individual ones. Does it solve that in a fundamental way? I don't know. It's to be seen.
How often is your false positive in the I mean, it depends on the length of the vector.
How
How
often?
often is the false positive?
False positive rate.
How often?
Yeah. You mentioned the room filter when you do the matching because it's try to use a kind of hashing function
Yeah.
to just compress the information.
Yeah.
And then scramble the worker. So I'm wondering how often is that?
Well, how often? I'm not sure what it means. How often
What's the percentage?
Oh, the percentage. Okay. That depends on the size of. There's some parameters in how you define the boom. Yeah, absolutely. It also So there's two ways that this scheme, the privacy scheme, creates false positives. One is by the sets. You know, the way that you transform messages into sets and predicates into sets. That even without the Bloom filter encoding produces false positives. Okay, number one. Number two, you have the Bloom filter. So if you have a Bloom filter of 4 bits, all bets are off, all false positives. But those are configuration parameters, and if you look at the analysis of Bloom filters, there's ways to figure out exact probabilities of collisions and false positives. Okay, I can give you my for.
The vector, the big vector.
Well, as I said, that's the parameter. Oh, you want to see this? We want to talk about the size? I experimented with Bloom filters of 1K, 1024, probably less than that also, between 128 and 1024. That's what I experimented with. Again, those can be large sets because in a message that has, let's say, 10 attributes, like the one that I was showing, okay, you have to add 2 strings per attribute. So you have 20 elements in the set. So, and I experimented with Bloom filters of 1, 2, 3, and I think 4 hash functions. But the best results are with the 1 or 2 functions. This is math that is well known in how you evaluate Bloom filters and how you construct Bloom filters. The other false positive part depends heavily on the workload. So, other questions?
Okay.
Thank you.
That's fine.
Thank you.